We have seen nature of power angle curves for two machine system with losses. Today we are going to learn about the effect of inertia on steady state stability of the power system. We know that the theory of steady state stability of circuits with resistance is complicated by the following facts. The first fact was maximum power at the sending end exceeds the maximum power at the receiving end and occurs at a different angular separation of the two machines. This case we have discussed in previous session as different nature of the power angle curves for different cases, right? The second, the maximum stable angle depends upon the relative inertias of the machines and upon governor action. Okay, let us justify this statement, that is the maximum stable angle depends upon the relative inertias of the machines. That means effect of inertia on steady state stability. This is very important. Many times in university exam it has been asked for not only 7 marks but having maximum marks near about 13 marks, right? So be attentive. For understanding the effect of inertia on steady state stability, we are going to consider the two cases. The case one is that the architrave impedance has positive resistance. Now we are familiar with this word architrave impedance. That means impedance of this branch which is connecting generator 1 to the motor 2, right? So the first case, when the architrave impedance has positive resistance, and obviously second case will be what? True. Second case will be when the architrave impedance has negative resistance, right? So let us start from the first, that is what will be the effect of inertia on steady state stability when the architrave impedance has positive resistance. Under this we are going to learn three different cases. Can anybody guess what would be those three different cases? Right. The first case will be that generator, that this is generator 1 connected to infinite bus. Second case will be motor is receiving the power from the infinite bus, and third case will be both these two machines will be two motors, that is generator 1 and this is motor 2. That means both are having finite inertias, right? So let us see one by one. Case 1. A generator of finite inertia to an infinite bus through series impedance with resistance. That means generator 1 which is having finite inertia fit into the infinite bus. For such case, the power curves are as shown. You are familiar with this nature of power angle curve, right? So the output of the generator is shown by curve P1 and the power received at the infinite bus by minus P2. P1 and this is minus P2 for generator, and this is for motor here, but here it is the case of infinite bus. Okay. If the power input to the generator is slowly increased, the generator voltage is advanced in phase, thus increasing the angular separation delta. It is true, right? Then the output of the generator increases so as to equal its input until P1 reaches its maximum value at delta is equal to delta M1, which is less than 90 degree, right? As it is clear from this power angle curve, this delta M1 which is greater than 90 degree. Okay, then therefore the system is stable for all positive values of delta less than delta M1, right? However, maximum power is received by the infinite bus at delta which is equal to delta M2 which is less than 90, which is less than delta M1. It is clear from these power angle curves, this maximum power received at the infinite bus at delta M2 which is less than 90 degree and less than this delta M1, right? Therefore, by definition, the steady state stability limit is the maximum value of received power, that is minus P2, and this occurs at delta equals to delta M2. The system is stable at this angle, right? So this was the first case when the generator connected to infinite bus. Okay, then come to the second case. Second case, motor of finite inertia receiving power from an infinite bus through series impedance. As shown in this diagram, the motor of finite inertia receiving power from the infinite bus. Okay, with the again positive series resistance, through positive series resistance. The nature of power angle curves as shown here. Now, in this case, P1 is the output of the infinite bus, right? And minus P2 is the input of the motor, correct? Let the shaft load on the motor be slowly increased. Now, what we are going to do? We are increasing the shaft load on the motor slowly. Okay, the motor voltage is retarded in phase. Yes, it is true. It is obviously correct. Thus, increasing delta, and the input of the motor increases so as to equal its output until minus P2 reaches its maximum value at delta is equal to delta M2. Here delta is equal to delta M2. Now in this case, which is less than 90 degree, right? If the motor load is further increased, synchronism is lost. Yes, if the motor load it is further increased, that means this delta M2 crosses 90 degree, then the system is losing its synchronism, right? So in both of the preceding cases, the stability limit is the maximum value of minus P2, which occurs at delta is equal to delta M2, which is less than 90 degree. In the case of finite motor, synchronism is lost if delta exceeds this angle. But this was not true when the case 1, that is when the motor 2, in case 1 as we have seen, the motor 2 was infinite bus. The synchronism was not lost because at that time our stability limit was at delta is equal to delta M1, which is greater than 90 degree. Okay, so what we are saying, in the case of finite motor, synchronism is lost if delta exceeds this angle, but in the case of finite generator, delta can increase from delta M2 to delta M1 with an accompanying increase in generator output P1 before synchronism is lost. The generator therefore is more stable when operating at stability limit than the motor is. This is the bottom line of our today's discussion, that the generator is more stable when operating at the stability limit than the motor is. True? Then come to case 3. Here a generator and motor both of finite and not necessarily equal inertia. Both are now finite machines. Right? It would be expected that the maximum stable value of delta would be greater than delta M2 but less than delta M1, and that the exact value would depend upon the relative inertias of the two machines. Now in this case, the value of stability limit depends upon the relative inertias of these two machines. Then what it will be? It would be being near delta M2 if the inertia of the generator were high compared with that of the motor, and it will be near delta M1 if the reverse were true. That means if the motor inertia would be greater than the generator inertia. Okay, and maximum of this curve obtained at an angle, that is delta is equal to delta C, which is given by the formula tan inverse M1 plus M2 upon M1 minus M2 into tan theta 1 2, where M1 and M2 are the inertia constants of the two machines and The critical angle delta C is always between the angles of maximum sent and received power. This delta C, it is always between delta M2 and delta M1, right? And here what are these M1, M2? These are the inertia constant. And what is this theta 1, 2? Can anybody tell me? Yes, true. It is the angle of architrave impedance, right? Okay. So what we are saying, it approaches delta M2 if M1 is greater than M2, much greater than M2, and it approaches to delta M1 if M1 is much less than M2, right? Okay. In each of the three cases considered above, all of which are for positive series resistance, the steady state stability limit is reached at delta is equal to delta M2. However, it appears that delta can increase beyond delta M2 up to a value of delta C before synchronism is lost. Thus, at maximum received power, there is a margin of stability which depends upon the relative inertias being greatest when machine 2 is an infinite bus. Right? This is true. Okay. So this was the first case when the architrave impedance was having the positive value. Now consider the second, when the architrave impedance has negative resistance as shown in this diagram. Then the situation is somewhat different if the series resistance is negative. The power angle curves are as shown. Okay. So here the maximum sent power is reached at a smaller value of delta than that for maximum received power. That is delta M1 is less than delta M2. From the observed from these power angle curves. It is therefore necessary to investigate whether the system is stable at values of delta between delta M1 and delta M2. Right? Again we are going to see here three cases. Case 1. If the motor is an infinite bus, the generator pulls out of step at delta M1 before minus P2 reaches its maximum value. Right? The stability limit is then the value of minus P2 at delta is equal to delta M1. In this case, the stability limit will be what? Delta is equal to delta M1. For the first case, that is when the generator connected to infinite bus. Okay. Then case 2. If, however, the generator is an infinite bus, now the motor is receiving the power from the infinite bus. In that case, the motor pulls out of step at delta M2. In that case, it will loses its synchronism at delta M2 where minus P2 is greatest. The stability limit is greater for infinite generator than for the infinite motor. Okay. Then case 3. If both machines are finite, the system would appear to be stable for all values of delta up to delta C computed from the equation, this same equation as we have seen previously, that is delta is equal to delta C, which is equal to tan inverse in bracket M1 plus M2 upon M1 minus M2 into tan theta 1 2, and lying between delta M1 and delta M2. Right? This delta C, it is lying between delta M1 and delta M2. For case 3, that is when both the machines are finite machines. Then the stability limit would then be value of received power at delta is equal to delta C. The received power would be less than its maximum value but greater than its value at delta is equal to delta M1. Right? Okay. So that's all for understanding the effect of inertia on the steady state stability. Okay. So what we have seen to understanding this effect of inertia on steady state stability, we have considered two different cases. That is whether the architrave impedance is positive or whether it is a negative. Right? For both the cases, we discuss three cases again. Three cases for each one. Okay, so for when the architrave impedance was positive, we consider the three cases. The three cases mainly was when one machine it is infinite bus, that is generator connected to infinite bus, first case. Then second case, motor it is receiving the power from the infinite bus, and third case, both the machines are finite. Right? Accordingly, we have seen the where the steady state stability limit it is occurring, whether it is at delta m1 or at delta m2 or in between delta m1 and delta m2, that is at delta c. Okay, we found that the stability limit it is greater when the second machine is infinite bus. For case 1, that is when the architrave impedance is positive, and it is exactly reverse for the case when the architrave impedance is negative. Right? Understood? Okay, that's all for today's session. Thank you.